So let's start with a new topic, that is GAN, Generative Adversarial Network. Now, generative artificial intelligence is an artificial intelligence capable of generating text, images, or other data using generative models, often in response to prompts. Generative AI models learn the patterns and structure of their input training data and then generate new data that has similar characteristics. Generative AI focuses on creating new and original content, chat responses, designs, synthetic data, or even deepfakes. Deepfake is getting more popular more because of its mimical uses. It's particularly valuable in creative fields and for novel problem solving, as it can autonomously generate many types of new output. Deepfake is generally a video of a person in which his or her face or body is digitally altered so that he/she appears be someone similar to the real person, typically used with the malicious objective. It may also be used to spread false or misinformation or rumor. The mechanics of the basics behind this technology is GAN, that is Generative Adversarial Network. So let's try to understand what is GAN. A GAN is a class of machine learning framework and a prominent framework for approaching generative AI. The concept was initially developed by Ian Goodfellow in 2014. A generative adversarial network is a deep learning architecture that consists of two neural networks competing against each other in a zero-sum game framework. Zero-sum is a situation often cited in game theory in which one person's gain is equivalent to another person's loss. So the net change in wealth or benefit is zero. The goal of a GAN is to generate new synthetic data that resembles some known data distribution. So what is generative adversarial network? GANs are a powerful class of neural networks that are used for unsupervised learning. GANs are basically made up of a system of two competing neural network models which compete with each other and are able to analyze, capture, and copy the variations within a dataset. So why are GANs developed in the first place? It has been noticed most of the mainstream neural nets can be easily fooled into the misclassifying things by adding only a small amount of noise and the original data. Surprisingly, the model after adding noise has higher confidence in the wrong prediction than when it predicted correctly. The reason for such an adversary is that most machine learning models learn from the limited amount of data, which is a huge drawback, as is prone to overfitting. Also, the mapping between the input and the output is almost linear, although it may seem that the boundaries of separation between the various classes are linear. But in reality, they are composed of linearities, and even a small change in a point in the feature space might lead to the misclassification of data. How do generate GANs? How do GANs work? Generative adversarial network can be broken down into three parts. That is generative, to learn a generative model which describes how data is generated in terms of a probabilistic model. Adversarial means the training of a model is done in an adversarial, different or opposite parameters settings. Networks use deep neural network as artificial intelligence algorithms for training purposes. So in GAN, there is a generator and a discriminator. The generator generates fake samples of data, be it in image, audio, or video, etc., and tries to fool the discriminator. The discriminator, on the other hand, tries to distinguish between the real and the fake samples. The generator and the discriminator are both neural networks, and they both run in competition with each other in the training phase. The steps are repeated several times, and in this, the generator and the discriminator get better and better in their respective jobs after each competition. The work can be visualized by the diagram given below. Here, the generative model captures the distribution of data and is trained in such a manner that it tries to maximize the probability of discriminator making a mistake. The discriminator, on the other hand, is based on a model that estimates the probability that the sample that it got is received from the training data and not from the generator. The GANs are formulated as a mini-max game where the discriminator is trying to minimize its reward V, D, G, and the generator is trying to minimize the discriminator's reward in other words, maximize its loss. It can be mathematically described by the formula given below, where G is generator, capital D is discriminator, P data, that is distribution of real data, PZ is distribution of generator, small x is sample from P data, small z is sample from PZ, and capital DX is discriminator network, and capital GZ is generator network. So generator model is trained while the discriminator is idle. After the discriminator is trained by the generator, fake data of the generator we can get its prediction and use the results for training the generator and get better from the previous state to try and fool the discriminator. Discriminator model. The discriminator is trained while the generator is idle. In this phase, the network is only forward propagated and no back propagation is done. The discriminator is trained on real data for n epochs and see if it can correctly predict them as real. Also in this phase, the discriminator is also trained in the fake generated data from the generator and see if it can correctly predict them as fake. Now different types of GANs model. Vanilla GAN. Now this is the simplest type of GAN. Here the generator and the discriminator are simple, multi-layered perceptron. In vanilla GAN, the algorithm is really simple. It tries to optimize the mathematical equation using stochastic gradient descent. Conditional GAN, that is CGAN. CGAN can be described as a deep learning method in which some conditional parameters are put into place. In CGAN, an additional parameter Y is added to the generator for generating the corresponding data. Labeling are also put into the input to the discriminator in order for the discriminator to help distinguish the real data from the fakely generated data. Deep convolution GAN, DC GAN. DC GAN is one of the most popular and also the most successful implementation of GAN. It is composed of conv nets in place of multi-layer perceptron. The conv nets are implemented without max pooling, which is in fact replaced by convolution stride. Also the layers are not fully connected. Laplacian pyramid, that is LabGAN. The Laplacian pyramid is a linear overtable image representation consisting of a set of band pass images spaced an octave apart plus a low frequency residual. This approach uses multiple numbers of generator and discriminator network and different levels of the Laplacian pyramid. This approach is mainly used because it produces very high quality images. The image is downsampled at first at each layer of the pyramid, and then it is again upscaled at each layer in a backward pass where the image acquires some noise from the conditional GAN at these layers until it reaches its original size. Super resolution, that is SR gain. SR gain, as the name suggests, is a way of designing GAN in which a deep neural network is used along with an adversarial network in order to produce high resolution images. This type of GAN is particularly useful in optimally upscaling native low resolution images to enhance their details minimizing errors while doing so. Advantages of generative disadvantage and adversarial network. Synthetic data generation. Now, GANs are can generate new synthetic data that resembles some known data distribution, which can be useful or data augmentation, anomaly detection, or creative applications. High quality results. GANs can produce high quality photorealistic results in image synthesis, video synthesis, music synthesis, and other tasks. Unsupervised learning. GANs can be trained without labeled data, making them suitable for unsupervised learning tasks where labeled data is scarce, or difficult to obtain. Versatility. GANs can be applied to a wide range of tasks, including image synthesis, text-to-image synthesis, image-to-image translation, and anomaly detection, data augmentation, and others also. Disadvantages of GAN, that's training instability. GANs can be difficult to train with the risk of instability, mode collapse, or failure to coverage. Computational cost. GANs can acquire a lot of computational resources and can be slow to train, especially for high resolution images or large data sets. Overfitting. GANs can overfit the training data, producing synthetic data that is too similar to the training data and lacking diversity. Bias and fairness. GAN can reflect the biases and unfairness present in the training data, leading to discriminatory or biased synthetic data. Interpretability and accountability. GANs can be opaque and difficult to interpret or explain, making it challenging to ensure accountability, transparency, or fairness in their applications. Thank you.